So my name's Lorenzo. Today I'll be going through Lab 6, Faraday's Law. Whoa, hold on. Okay, so the introduction. So the purpose of this lab was to see what happens when we drop a bar magnet through an aluminum foil tube through Faraday's Law, and then we determine how a change in magnetic flux creates an EMF, which induces a current. And our results showed that the real world experiment was had an average time of 1.14 seconds, while the computation model had a time of 0.495 seconds. So the main physics concepts that were used was one, the Biot-Savart law, which calculates the magnetic field of a dipole, depicting the bar magnet as a dipole, and then Faraday's law, which demonstrates change in magnetic flux produce or shows that the change in magnetic flux produces an EMF, and then Lenz's law, which shows that the induced currents created by that oppose a change that this reflects why the magnet slows down. So in our experiment, we treated the system as a magnet and tube, and everything else was a surrounding. Then after determining the north end of the bar using the magnetometer, we hold the aluminum tube vertical and drop it. And these results, and that we eventually came to an average of 1.14 seconds. So we couldn't use a Ferris tube such as a steel pipe, is because like the magnet would be too attracted to the side, so it wouldn't fall through. And then what happens to the magnet? Well, it falls through much lower than it would have in the free space as a result of Faraday's law. So this is my glow script code. These are just the constants. The one thing we had to search up was like the aluminum resistivity, and then we had the tube length, wall thickness, and then the inner radius. And then we also had the magnet properties, which we determined in the previous lab, so that we had like the dipole moment magnitude and the weight. And these are some of the simulation settings we had just so we could like integrate across and everything. And then I just plotted the velocity versus time graph. And then this pretty much made the cylindrical magnet. This determines the magnetic field, and then this determines the change in magnetic flux over time. And then this was our main loop, and then we set those for when it entered and exited, and then we also like iterated across. So like when it was like going down the rate, it would like increase in time and everything. And then we also had demonstrated like the force of gravity as that. And then we also had an imposing force. So we use that, which is the induced current from Faraday's law, and then the force magnitude on the ring from the dipole, and then just the F net, which should be the gravitation force minus the vector, which should be like the force of magnitude on the ring from the dipole. And then we just put that into the graph. So this was pretty much our simulation, and this pretty much shows the magnet, and then the blue thing shows the currents, and then this is velocity versus time graph. As you can see, it starts off by decreasing. The velocity decreases in a negative direction as it goes down to the magnet, and it pretty much like becomes a constant velocity. So at one point in the tube, the gravitational force is equal to the magnetic force there, and then the equals kind of when it exits the tube. So interpreting the simulation. So the coloring on the tube indicates the magnitude and direction of the current flowing through. The red indicates the counterclockwise current, while the blue indicates the clockwise current. And this demonstrates Lenz's law, as induced current will flow in a direction where the magnetic field opposes the direction to change of flux. And if we flip their magnet around, the induced current runs in opposite directions more, but the magnitude will still be the same. So the computational model falls faster than a real-world system. The computational may be more accurate due to the cardboard inside of a lumen tube, which may interfere with the current and the magnet. And then the shape of the velocity for the time graph shows that the velocity is negative as it has a negative slope when not in tube, meaning that the forces are increasing in the negative direction, and thus the downward force of gravity is stronger than the opposing magnetic force. However, in the tube, velocity is constant, so the forces are also constant in this tube. So obviously the computation model was much faster, but they're generally in the same ballpark. And then some of the possible source of errors this was that our physical system may have lacked positions with lack instruments. For example, use a phone for the cordings, and they may not have been accurate with our droppings and everything. So being off by a few like 3/2 seconds. And then the cardboard and the tube may have interfered with the currents and the magnetic fields on that. And then we also used the calculation for the magnetic dipole moment of the magnet from the previous lab. And this was obviously a different magnet. So there could have been a lot of errors in there. Like we didn't actually have the full weight of it. We just used what we had from data before. And then if the resistivity of the conductor were reduced as close as possible to zero, how would like this would cause the magnet to fall less quickly through the tube as the resistance decreases because the magnetic force would be closer to gravity, so the magnet gets like a tube. And it's shown by the current equals EMF over R. And if holes or slots were cut into the tube, then there'd be less aluminum to create an induced current on the magnet, so there'd be less current and thus less force, resulting in faster magnetic magnet fall.